Okay, I'm going to begin because I'd like to keep some time to work this period. So, we're going to talk about force versus time graphs. I sent out a message yesterday. I'm going to guess that many of you didn't get it or what have you. That's okay. Hey? Not in class. On your own time, sometime? I don't want you to miss any more time. So this is on page 283 in the book if you want to follow along, and it's really, really simple. It's probably the last simple thing we're going to do in here. Okay? So these are our notes, so I highly encourage you to make good choices and put those phones away and, pay attention so you don't have to study it later, because if you just learn it now, you don't have to study it later, because you'll learn it now. Glad you're paying attention to that, Dad. I learned that about second month of university. All you gotta do is pay attention in class, and you don't have to study.
What's your thoughts on the strike right now?
The strike? Oh, don't draw the graph.
Why?
Don't draw the graph.
Why not?
It's just there as a visual. Don't draw the graph.
Well, how much is it?
Not much. I've got like 5 slides. Yeah, those are questions actually. I'll hand out questions at a time. Okay, so force versus time graphs from page 283. Determine the impulse and the area under a force time graph. Include constant positive and negative force and uniformly changing force. So once again, we are looking at a graph, and this time it's a force versus time graph. So when they say constant positive, that would be that one, right? That's constant positive. Constant negative would be, doesn't exist here, does it? Right? Uniformly changing would be that one, that one, that one. Those are all uniformly changing. They're all angled. The only ones that are constant forces are flat. So like constant negative would be like that, right? Yeah. So in other words, you're not going to see any curvy ones. Okay, so if a constant force acts over a time, the basic graph will look like this one. Right? Constant force, the force remains the same. Force multiplied by time is the area under the graph. Force is the height of the rectangle, and time is like the length and the width, right? So the area is force multiplied by time, right? On a rectangle kind of graph like that, right? And what is force multiplied by time? Well, we know that that is the impulse. It's probably a little too small, isn't it? The font. Force multiplied by time is the area of the graph, and we know that impulse is defined as the force multiplied by the time. Therefore, logically, the area under the graph then is defined as the impulse. Now, is that true even if it's not a rectangle? Absolutely, right? Who cares if it's a rectangle? Doesn't matter. The force multiplied by the time is the impulse, and that is the area under the graph, so therefore the area under the graph then is defined as the impulse. Okay. What I wanted. So, in most cases, now that's sort of the generic, basic, easy, simplified version. Now, in most cases, the force is not constant. Very rarely is a force constant. It will increase as colliding objects are compressed, and decrease as they move away from one another, right? So like when you hit a baseball or with a racket, hit a tennis ball, the ball compresses, and as it compresses, the amount of force increases, and as it moves away from the racket, it expands, and the force is less, right? And so you would likely get a graph that kind of looks like that. The force increases, and then the force decreases. Do the numbers here matter? No. And again, the area under the graph is equal to the impulse. What's the letter that we use for impulse? J. J is F times T. Okay, so there's the compression part of the interaction, and then there's the rebound part of the interaction. In the compression part, the force will increase, and in the rebound part, the force will decrease. So as an example, what would be the impulse in a situation like this? What is the impulse? How do we do it? Find the area. It's a triangle. What's the formula for area of a triangle? Base times height divided by 2, right? So the base is from 0 to 1.2. The height is up to 25, it looks like. Divided by 2. So how much? 15 newtons? 15 newton seconds, correct. That is the correct unit for impulse, newton seconds. Remember, there was a few people, who was all the way Friday? Lauren? Okay, so quickly, what happens when I'll do a review for everyone else. What happens when you follow through with a swing on a tennis racket or a hockey stick or a baseball bat? You're increasing Exactly, you're increasing the time. So in other words, you're stretching this out, which makes a greater impulse, right? So I'm just going to do this here, right? So in the F delta T, or fat equals MAV formula, right? When you increase the time, but keep the force, the mass of an object generally stays the same. So if the time increases, what has to happen to the velocity? It has to increase the change of velocity, which, it's kind of like a negotiation, right? Like the university's doing, right? If the one side gives more, then the other side, to make it balanced, has to give more, right? So that increases the velocity, which means it goes farther. That's why you follow through, right? The opposite is with the car crash video that we saw. Why did they make that crumple zone out front? Gives you more time to slow down. So if you increase the amount of time, if the velocity remains the same, right? Because you can't change the change in velocity. Like if you're doing 100 and you got to become stopped, the delta V is minus 100, right? The mass of the car doesn't change. You can change the amount of the time. So if you change the amount of time, what does that do to the size of the force? Makes it smaller. As the time increases, right, the force becomes smaller, which means that the person in the car survives. Less force on it, right? If I fire a ball at Dan and he goes to catch it, should he put his hands out like this to try to catch it? Or should he try to catch it and do this? Right? We've been taught that. Will's been taught that playing shortstop, right? You cradle the ball in like this. Why do you do that, Will? You give it more time, which means there's a much smaller force, which means it doesn't hurt as much, right? And it's more likely to stay in your body, right? If you are, and I wouldn't recommend that you do, if you become a boxer or like an ultimate fighter or something like that, when someone punches you, what is rolling with the punch? Anyone know what that means? Right? I'm not going to hit you, Will, right? If I decide to hit Will like this, right, and he moves his head back with the punch, what happens? Increase the amount of time that my fist is in contact with his face, and it will decrease the force. So it will hurt me less, hurt him less as well. Boxers do that all the time. Roll with the punches. You never understood that? There you go, you learned something, right? You're increasing the amount of time, decreasing the force. Okay, so is this the one that's on your page?
Yeah.
Oh, you do have that graph before. I apologize, I didn't realize that. Example number 4, determine the impulse for each of the given graphs. So here's one right here, figure 815a. I think you have it on the bottom there, that's right. Okay, so notice that the force doesn't go all the way down, right? So how are we going to do this? You're going to break it into a, rectangle and a triangle, right? How about we just call them, I'll call it J1 and J2. Impulse 1, impulse 2. J1 is a triangle, so that's going to be the base times height, so it looks like the base is 1. The height is from 20 to 70, so that's 50. Divide by 2 because it's a triangle. 25 Newton seconds. Straight 2 is a rectangle. The base is 1. The height is 20, which is 20 for a total of 45 Newton seconds. How hard was that? Pretty darn easy. Now, the textbook shows this, so just in case you get worried, well, listen. Okay? The outcome said uniformly changing force, which means at an angle, right? This one is non-uniformly. This is non-uniformly changing, okay? So it's got this bell curve shape to it. You guys know what the bell curve is? Yeah? Did you take some stats? Yeah? I wish, so anyways, generally, the graphs are not those nice, neat triangles. Generally, they're going to be curvy like that, okay? So this is actually more real-life varying force of a tennis ball, okay? This is non-uniformly changing. I'll not be requiring this. The only way that you could do that would be to, do you remember the lab back in grade 11 where you count the little squares? You'd have to do that here. Right? You'd have to count the little squares. You'd say, well, okay, there's a half a square, right? There's a half a square, and that half a square becomes a whole square, right? Or you could learn calculus. Once you do that, once you know the equation for that curve, then using integration skills, you can figure out the area. You're going to see that eventually, if you take calculus. Okay. So here's the assignment. I think, are there some on the back of that sheet there? What's on the back? Okay, so what I did was I've assigned page 287, number 6, A and B, page 308, number 50 and 51. Because I know you're going to be drawing on the graph, what I did was ran them off for you so you can draw on the graph. Okay? And I should also say, because I forgot to say this, I had it out on whatever day that was. There's a whole bunch of multiple choice questions. Does anyone have it sort of handy that I can show you what it's on?
Yeah, where are the answers?
Thank you. So I had students once say, Mr. Nana, I sure would like some more multiple choice questions. So I found these somewhere. I have the answers to them. Do you want me just to post them in school? Is that the best way to do it? Okay, so this kind of covers the whole unit. I should have mentioned that. I saw people starting this already. So you kind of use this as kind of a test sheet. I'll see when I'll find the answers in here. Okay? So your assignment today is that. Tomorrow we're going to get into the one-dimensional collisions. It's going to be a little step up, but it isn't two-dimensional yet. When you get two-dimensional, well, be ready.